Just going to give a quick overview here of using LuaRPC on embedded Lua. So up at the top here, we're defining an error handler that's going to be used by LuaRPC. All it does is just print out whatever error was passed to it. On this line here, we actually associate the error handler with the with our RPC usage. Next, we're going to connect over a serial port to an embedded Lua device. So there's a Lua instance running on there, and we connect to it. Now we do a garbage collection on the eLua device and print out the current amount of memory that's being used by garbage collectible objects in the VM. Now these are a set of aliases. These alias a bunch of functions into our local namespace. This is one of the main advantages of using LuaRPC, is that it basically treats the remote global table as a local table that we can call functions on and do various other operations. So here we set these up so that we can just call these functions as if they're a part of our local environment. So we call some setup functions to set up the CAN bus to the device we're controlling as if they're local functions, but they get executed on the eLua device. And now this function is used for requesting different parameters from the CAN device that we're controlling. And we request a couple of those parameters just to make sure that everything's sane on startup. This is an iterator that we're setting up. This allows us to loop over and get updated positions as we go along. So we return a function which each time it's called is going to update this I value, and it'll keep going until a particular time is reached, and each time it's called it's going to give us a new position value based on the formula that's on the line in the middle there. Now this is the main function that we're going to be calling, oscillate. It gets a position updated each time it goes through that for loop using the that pos iter. So it starts up a timer, then it sends out a command to the CAN device that includes a position, and then also the rate of change that we want it to fill in to interpolate between points between this command and the next one. Now we also note down our last position so that we know where we've been. And then we send a command that tells the CAN device to actually update and follow the position command that we just gave it. And then this, since the CAN device expects to get commands at a 100 Hertz rate, we just we set up a timer earlier in the loop, and this rounds out the rest of the 10 milliseconds that we need to wait before sending another position update. So down here, then we can actually send. Now we're actually copying the function, the pos iter, the iterator function, over to the embedded device, and we're doing the same for the oscillate function. So the code is compiled locally, and then the bytecode is dumped and converted for the embedded device, and then we can just call that function having sent it to the embedded device locally. So we set a couple of parameters here for controlling the amplitude and also the amount of time we want it to run for. So I switch over to a console, and I'm just going to call Lua and tell it to run this the script that we were just looking at. It's going to do all of those operations I just described. So it's printing out those parameters it's requesting. Now if we look over, you can see it updates and then starts following our command. So we have a superposition of two sinusoids here, and the control for that's actually being done in real time from the embedded Lua device that we're looking down at here. You can see at the bottom there's the CAN bus connector, and then there's an ST micro STM32 Cortex M3 microcontroller that's controlling it. So if we want, we actually stayed in the Lua interpreter here, and we can just call this function with different parameters. So we can adjust the frequency. So we just kicked it up a number of notches there. Change it to another frequency. You can see how we can just play with this iteratively and tweak parameters, and all that code is also dynamic. So if we wanted to change the code as well, we can, so you don't have to totally reflash any of the devices. We can play around with parameters interactively. So there we had a superposition of two sinusoids. We can get rid of that and just make it a single one and update it just by pasting it back in there. And then we can copy the iterator that's in our local Lua into the embedded device. So that's already copied over. And then we can run with a different set of parameters. So you can see it's now oscillating with just on a single sinusoid. Crank it up to a higher frequency. So you can see, again, it reduced the amplitude. The power that you get here is in that you don't have to wait for it to reflash. The size of the Lua code that has to be transferred over the serial connection is pretty small, so the updates don't take too long. They're basically instantaneous, and then so you can change the logic of your code, your algorithms on the fly, and have a much shorter amount of time between your idea and seeing how it works.